Okay, thank you for the kind introduction. I guess this is the clicker, right? Yep. Okay, so my topic might seem a bit technical for this time of the day because the happy hour is coming, so I really appreciate all of you coming here. The story here is that you have seen these amazing headsets like the Magic Leap 2, and we have the HoloLenses and Vario XR3. And listening to the talks here, it seems kind of that those things that just move from the design phase to the manufacturing and then they appear on the shop's shelves automatically. But what we are missing from the story is that there has been a lot of testing involved. And this is a story about testing, a very particular aspect of testing headsets or the components that make up devices like HoloLens 2. So for your convenience, this is the outline, so I will describe our company a bit so you understand why I'm qualified to talk here. And then we'll go to see how the diffractive waveguides actually work, just on a high level. And then what the customers require for the grating characterization. What are the requirements? And then I'll show the solution, which is the Littrow Diffractometer. And I prove that it works with some measurement results. So for the company, what we do, most of you probably have not heard about optofidelity. But we have 15 years of experience on precision, high-volume test automation, metrology, software, and mechatronics. So we have all of that in-house. We do complete test systems inside our premises. And specifically for this conference, we are the global market leader in AR, VR, and XR, and display optical metrology. For example, in the AR business, we have been doing testers for about 10 years already now. So we are really established there. For normal consumers, you will never hear about us, but if you visit the labs of the major players in the business, you will very likely see one of our devices or even several in the R&D labs or in the mass production lines. And we are based in Tampere, Finland, where I'm coming from, but we also have offices here in Cupertino, Redmond, and factory in China. So let's go into the technology itself. How do the diffractive augmented reality waveguides work? So by the way, that is one of our testers. One of our engineer is placing a headset on that tester, and you can actually see the tester in our booth 314 if you come and visit us. So without going into details, this is how the diffractive augmented reality waveguides actually work. So there needs to be a projector, but you cannot place the projector on front of your head or front of the eye, because otherwise you'll just see the projector and not the real world. So the projector has to be on the side, and you will transfer the image with this waveguide to your eye. Basically, the light is coupled into the waveguide, which is just a flat piece of glass with a grating, and then it's coupled out to your eye with another grating. Some magic might happen in between, but that's basically how it works. And the gratings are diffractive gratings. It means that it's just a periodic structure on the surface or inside the waveguide. And very importantly, the grating period, because it's a periodic structure, there's some period. That dictates which angles the light rays go into the waveguide. And that becomes very important later in this story. So for example, HoloLens 2 employs these kinds of waveguides, and that is the basic principle. And just to demonstrate that the basic principle is actually, in practice, not so basic, it's actually very complicated. This is an example design, not from any commercial headsets. It's just a reference design from one of our projects that we did together with Morphotonics, NIL Technology, Lightrans, and SHOT to demonstrate some new manufacturing methods that Morphotonics was developing. So you can see that this would be now in front of your eye, the piece of glass. So there would be your eye would be looking through the out-coupler grating, the big one at the top. But there's the in-coupler grating, the projector is attached to that one, and then there's the exit pupil expander grating. In many designs, they have 3 gratings processing the light, so to speak. And all of those grating areas, they can have different parameters, so the grating period can be different. Grating orientation is definitely different, so they are like one-dimensional grating lines, but some of them are like vertical in this image, some of them are 45 degrees oriented, and some are horizontal. Also, the cross-sectional shape of the grating can be very different. And inside even one grating, the properties might vary. So it's actually a complicated system. And then we go to the testing part. Okay, some designer has designed that, and then some guys want to manufacture it. Where does the testing come in? So if you are in the R&D phase of the development, okay, the designer has designed many kinds of designs. Some of them might not be manufacturable. Some of them might be easy to manufacture, but you have to be doing the testing. Which ones are the best that you could produce for the market? So you try different designs, develop your fabrication processes, and you need to be testing the gratings themselves. Is the grating exactly what the design calls for? Okay, then you end up finally in mass production. In mass production, typically you don't care anymore about the gratings because, well, the customer doesn't really care about your grating. She only or he only cares about the image quality. You put the headset in your head. Is the image quality good? Okay, you're good to go. You don't care about the grating period anymore. But in mass production, you are testing the waveguide and the image quality is not good for some sample. What do you do then? Then you have to check what is actually wrong with the waveguide. Probably it's something wrong with the gratings. Which grating? What parameter? You have to find out. So you absolutely must be able to characterize the grating. And what parameters does the industry want to be measuring from the gratings? As usual, the customers have a long list of requirements that what do they actually want from the gratings. Most importantly, maybe the grating period needs to be measured. And for example, the HoloLens team has publicly said that they aim for tens of picometers of grating period accuracy for the measurement, which might sound crazy, but that's what they want. And they also have the grating period ranging from 500 nanometer to sub 200 nanometer periods. You have to be able to measure the range. Then there's a grating orientation, as we talked about. They need to be exactly correct with arcsecond level repeatability accuracy. Sounds also pretty unbelievable, but that's what they want. They would ideally want to know also the cross-sectional shape and height, find some defects. There are different types of gratings that should be able to be measured. There can be different samples, materials, glass, there can be silicon wafers, polymer, nano imprint layers. All should be measurable. And definitely it must be non-destructive. You cannot cut the grating in half in the production line or like that. And fast, cheap, reliable, that's the usual story. But I mentioned picometers, so if you think about it, we are measuring a physical grating period, and then I say that I want picometer level accuracy. Well, the smallest atom is a hydrogen atom. Its size is 53 picometers. Now you are telling me that you want to measure some physical thing with picometer accuracy. So how did you actually make your grating? Because all atoms are much bigger than your picometer. So it doesn't make sense. But this is actually what the simulations say, that if the grating period is off like tens of picometers, then the properties of the grating change so much that it's no longer good. You need to be able to measure at that accuracy. But for example, typically things like this are characterized microscopes or electron beam microscopes. And you get resolution of nanometers, which is thousands of picometers already. So it's completely impossible requirement for any microscopic technique. Okay, now we have the list of impossible customer requirements. What do we do now? Okay, the solution that I'm proposing that we have about 10 years of experience with is a Littrow diffractometer. And this picture is actually not from the Littrow diffractometer. It's again one of our test systems that you can see in our booth, temporal tester. But okay, I showed you earlier that if you have a diffractive grating, you put a light beam in, and it splits the light beam into several beams that go into different directions. And the directions depend on the grating period. So you start thinking, okay, I shoot the sample with the laser and see what angle the laser comes out and measure the angle. and then I'm done, right? It's very simple. But then you start figuring out what kind of accuracy you need for the angle measurements, because angles are quite difficult to measure. So you end up with something like this room-size system that, okay, shooting the laser to the other wall, and maybe I get some kind of enough accuracy for the angle measurement, and it's not practical at all. So what we do is go around it. So it so happens that if you shoot the sample with the laser and rotate the sample, so the laser is split into several beams, but if you rotate it properly, one of the beams will actually come back to the laser, exactly back to the laser. That's kind of a special condition. Only happens at one rotation angle of the sample, or tilting angle. And with very simple mathematics, you can then, if you know the wavelength of the laser and the angle of your sample rotation, there are accurate stages that will tell you that angle very accurately. Then you can calculate, hey, okay, the grating period for this sample must be exactly this. And you can do that extremely accurately with this very simple mathematical equation. Of course, this is widely simplified, but that is the essence of the story. And actually in this picture, so we shoot the sample with the laser. The light is diffracted back at the Littrow angle, but we have a beam splitter and a camera, so we can detect with the camera exactly when the laser light comes back to the laser. And yeah, so we can detect this special condition. And we also, in this picture, we just have one rotation stage, but we could have two rotation stages, so we can rotate the sample along the surface normal or around that. So in this picture, the sample grating lines must be vertical for us to be able to do the measurement. So at the same measurement, we are also measuring the relative grating angles, because different gratings, if you remember, have different grating line orientations, and the orientation has to be vertical for this measurement to work, so you are also measuring grating line orientation at the same time as a bonus, just for free. Very convenient. It's extremely important to have the proper laser there, because the laser wavelength is the measuring stick that we use here. So if the laser wavelength is not stable, it means that our measurement system directly has that same error as the laser wavelength does. But luckily, there are lasers that are extremely stable on the market. They have a picometer level stability, which is exactly what we need. So even when the temperature changes, the laser wavelength does not change more than a picometer. And naturally, we need a narrow line width, otherwise we get a spectrum on the camera. And interestingly also, we must select the laser wavelength so that we can measure the exact grating period that we are looking at. Otherwise, the Littrow angle goes over 90 degrees, and then, well, we cannot measure reflection if the sample is rotated 90 degrees. Makes sense. So this graph is explaining to you which kind of laser to use with what kind of grating periods. How to build the system then? This is one example. So basically, you need ways to rotate the sample. Then you need a way to move your laser so that you can hit any point on the sample, so you can scan the sample that way. And this is one way to build it. So you put your laser on an XY stage, and then you have double rotation stages on the sample then on the right. And the laser stage then houses the measurement head, the camera, and the beam splitter, and the laser. And the sample rotary stack then needs to be very high repeatability, arcsecond level repeatability stage. But luckily, also those are available on the market. They are pretty expensive, but they can be bought. And the measurement camera is actually nothing special. But the important thing about that is, as I mentioned, we are measuring exactly when the laser is coming back to the laser itself. So it acts as a zero detector. We don't measure any angles there with the laser itself. And that's kind of a shortcut to make this system very, very accurate. Okay, now I have shown that there could be this kind of Littrow system. It looks pretty simple, but can we actually measure something with it? So just a few example results. We can not, of course, share anything confidential, but luckily the sample I described to you earlier it's kind of open in that sense that it's not a secret design for anybody. So we can measure that and share the results. the key question here is that how do we test the test system? We build a test system, but we need some system to test the test system. Is it now accurate and repeatable? And the way we do it is we measure the repeatability of the measurement. So we basically measure the exact same thing many, many times and expecting the same result. Otherwise, the measurement system is useless if it produces different results every day and with different operators. So in this case, we have just measured 1 point on one sample 10 times. And we notice that the period measurement is repeatable within 6 picometers, and the relative orientation of the grating lines is repeatable within 2 arcseconds with this sample. So this is actually a very representative measurement. This is what we typically get with these systems, and we can even get much better. This is a pretty standard, simplified setup, so we can even increase the repeatability. Okay, if the system now works, what can we do with it? So this is, for example, that second grating that I showed you, the pupil expander grating. Now, because our laser moves, we can scan all the points in the grating and see are the grating properties the same everywhere. That is very important. So the numbers are not important to see, but the color maps the grating period in different places. So for example, you can see this one almost black spot. So suddenly there's one spot on the grating that the grating period is very different than the other spots. Something has definitely gone wrong in the manufacturing process. But for example, here the standard deviation of the grating period is 0.0075 nanometers, which is 7.5 picometers. That's the standard deviation. So pretty nice manufacturing, but clearly 1 point is not good. And then we can do the same for the orientation. So the grating lines, are they straight everywhere, or are they curved? Some manufacturing processes like laser interference lithography typically produce curved grating lines. But here we see again that that one single point has a bit different orientation than the others. Again, we are talking about arcsecond level differences, so it is a really minor difference, but we can very clearly see it now. Okay, let's summarize so that we can join the happy hour. That is very important. I hope that I have convinced you that the Littrow diffractometer has many advantages. It has extremely high repeatability and accuracy, just insane levels, picometers. That's crazy. So relative orientation also can be measured with arcsecond level accuracy. That's also crazy. It also detects some defect types. So if you get no light back to the sensor, okay, there must be something wrong with the grating. It didn't even diffract light back to the camera. And we can measure any grating type actually, so any material even, and 2D gratings are no problem. It's a diffraction grating, it always will work with the Littrow diffractometer. And it's definitely non-destructive. You are just shooting the sample with a very low power, eye-safe laser. There are, of course, if we are fair as engineers, there are many limitations where you might consider other techniques that I have listed. So grating shape, which is very important, cannot be measured with a Littrow diffractometer. For that, you would want to use interferometric methods or microscopy, or then scatterometer and inverse diffraction methods. Also, diffraction efficiency, you can kind of measure it, but not very accurately. And very important point that I have completely neglected is that all the mechanical stages, they have errors in their motion, and they need to be compensated. Some of them are really difficult to compensate, but there are many solutions. And also sample bending can have effects if you mount it improperly. That changes your numbers. It's a pretty slow method. Well, it's very accurate, so you can guess it's slow and expensive. Rotary stages are very expensive. So to conclude, I have tried to explain to you that if you are making these waveguide gratings, you absolutely need a way to measure the grating properties extremely accurately, both in R&D and in production. And the Littrow diffractometer is actually the only practical way of doing it with the accuracies that I have described that the customers need. And it seems on paper that the system is pretty simple, just buy a good laser and some rotary stages and you are all set. But then you start thinking that, what about all the errors in the motion, in the wavelength of the laser and things like that? And you have to compensate for everything and be sure that you are doing it properly. That is the expertise that you need there. Okay, finally I need to acknowledge my colleagues. So Rosa Mäkitalo has done all the measurements here, and Mikael Jokinen has been working on the topic for many, many years. And also I would like to thank More Photonics Light Transnil Technology and SHOT for the measurement samples that were used for this study. So with that, I will conclude and invite you all to the booth 314 to see completely different types of test systems and maybe discuss more about also this one. And well, thank you very much, and I'm now happy to answer all your questions.
Okay, this is a really short question. Could you, in simple plain English, 3 sentences or so, explain pupil expansion? It's something that I've personally tried to study, and it's really hard for me to comprehend.
Oh, that is a very difficult topic to explain quickly, but I try. So pupil expansion is the point that you have a projector that makes only one pupil, like a binocular. So your eye needs to be in exactly one spot if you look at the projector itself. But of course, the user of a headset, the eye can be, distance between eyes is different, so different users have different needs. So what the waveguide does is actually it takes copies of that pupil. It copies it around, so in X and Y, so you get a matrix of those pupils. You are not expanding one pupil as in a bigger pupil, but you are making copies of that pupil so that in effect it becomes a big pupil. So then your eye can be anywhere in the eye box of a HoloLens. You can just pick it up and you will see the picture. You don't have to position your eye exactly in the proper spot. That is how it goes in a very high level, but the details are very complicated.
It's a really short follow-up. So pupil, in that sense, in that context, is not the physiological pupil? Like, because are we drawing a line between a, tactile execution, right, of light, or versus a human factor? So is it not physiological, that term, pupil?
Yes, the pupil is the optical design terminology pupil. So, of course, your human eye has the pupil. That is where the term comes from. But if you look at any kind of optical system, the output pupil of that system must match with your pupil. Otherwise, the light just goes somewhere else and it doesn't even hit your eye. So all optical systems, like a telescope, if you imagine, it kind of focuses the light into a small spot, which is where your eye should be, so that you see something. It's a very narrowly defined spot where you see something with a telescope. But, headsets cannot work like that. You need to have a large eye box where your eye can be. Yeah, that's how it works. Thanks for the good question. Any other questions? We still have 1 minute. Okay, in that case, I thank you very much, and let's go and enjoy the happy hour. Thank you.